In this video, we're going to talk about pseudo-random number generator, and this is a feature in many programming frameworks, including C++, which supports it natively through CSDT library. In the next couple of slides, we're going to talk about how to generate pseudo-random numbers in C++, and this applies in C as well. So a pseudo-random number generator is also known as deterministic random bit generator. I know this is a lot. It's basically an algorithm for generating a sequence of numbers whose approximate the properties of sequences of random numbers. So there is no true computer out there that is capable of generating a truly random number in computer science. But what we can do is make use of this library to enable some sort of pseudo-random number generation, which is completely determined by an initial value. And this is the value called seed, S-E-E-D. So before we get into that, just note that in C++ and C, there is a macro called rand_max. This random max is a platform-dependent value that is guaranteed to be at least 32,000 on any standard library implementations. So on a 64-bit Mac, on an Eclipse running GNU G++, this number is this much, which is this big number. Question, how do you generate a random value between 0 and n-1? Or the other question, how about generating a random value between 1 and n? If we look at the first problem, generating a random value between 0 and n-1, assuming ren, which is the function, that gives us the random number, and this number could be really, really big. If you want anything in between 0 and n-1, this is what you do. Is that correct or not? Well, let's take a look. If we mod anything by the value n, what we're getting in is 0 all the way to n-1. This is by definition of a remainder, right, in a standard mathematic division. How about generating a random value between 1 and n? And notice that 1 is 0 plus 1, right? And n is n-1 plus 1. So in order to make this work, the answer to the second one should be 1 plus ren mod n. Hopefully this is clear. Let's go through some definitions here. You can go to this link in particular to find out more about the definition of random or this randomizer function. Essentially how this works is, remember what I said, for any pseudo-random number generator, its ability to generate a random value depends on an initial value, and this is what we typically call a seed. For any platform in which you're running this random generator on, that platform could be a Macintosh, could be a Windows, could be Solaris, etc. This operating system maintains a list of some pre-built or predetermined integers that appears to be random. So this is a list of numbers sitting in it. There is an algorithm that generates a series of non-related integers from that list. And this algorithm then requires the use of some sort of initializer, which is this seed value we're talking about, to start reading from that list at a different spot each time. We won't get into the specific algorithms that is in use. You can typically look it up. There are many open source code that illustrates these algorithms. However, that is beyond the scope of our discussions here. Question, how do we seed our randomness? So this begs a question. We have to make use, first of all, this srand, which is called seed randomizer, with an initial seed value. The question is, what should this value be? To answer that question, let's move on to the next slide. The definition of this srand or this API is located here. Let's take, for example, we're going to use a value of 100 for the seed. This literally reads seeding or reading starts at integer position 100 in that list of built-in integers. In reality, this algorithm is a lot more complicated than this, but let's just use this as context. Therefore, we need to change the seed each time a program is run. Why? Because you don't want to start randomizing your generator each time with a value of 100, because that means there is predictability. Therefore, we need to find a pseudo-random number that is different each time when a program is run for this value. So what can we do with this value that is different each time? Well, one of the things that we do in the industry is we can use our current time. And when I say current time, this is the total number of millisecond transpired since January 1st, 1970. So in Linux, there is this epoch that you can use. When you call upon this epoch, this time function that allows you to call it gives you a value. And this is a very large number that simply returns the number of seconds or milliseconds since January 1st, 1970, given your current time. And of course, your current time is governed by the clock in your machine. But suffice to say, every time, let's say if you're using the same machine to run your code, your seed, which is coming off of this time function, which gives you the current time, or in epoch, since January 1st, 1970, is going to be different each time. So this allows you to seed your randomizer. The need to have to srand only needs to happen one time per program run. Let's say if you have to call your randomizer 10,000 times in the course of your business logic, you only need to srand or seed your randomizer once. The mistake that the students make is that they will seed their randomizer every single time they need to call ran, which is not very, very efficient. You don't want to do that. Anyway, there is a lot of problems that deals with generating random numbers. And of course, there is no randomness or true randomness is in computer science. So at best, we're talking about pseudo-random number generations. As such, there's a lot of examples out there on the web. We will constrain the scope of our discussion on this topic and leave you to some of the practice problems that you will find at the end of your lecture, such as rolling a dice. Let's generate a random roll outcome, or let's say rolling a dice 10 times. Let's generate a random roll each time. How would you do that? Making use of ran and srand. I'll leave you guys to those practices.